Hey everyone, Mr. Smith here, and in this video lesson, it's going to be a bit of a shorter one. We're going to look at the experiment that helped us determine the charge on an electron or proton, otherwise known as the elementary charge. And that experiment is called the Millikan experiment from Robert Millikan. So let's get started. So the ideas behind this elementary charge, the driving factor behind trying to find it was that there existed some smallest unit electric charge, which others are simple multiples. So I think at this point, Robert Millikan, scientists, had an idea. There was, charge just can't be divided up infinitesimally small. There was like some building blocks of charge, and you could only have charge in certain amounts. And there was the smallest unit of charge. They wanted to find it. And that smallest unit of charge corresponds to the elementary charge. This is the charge on an electron. It's negative, and it's charge on a proton if this value is positive. 1.602 times 10 to the minus 19 coulombs. So as it's written down here, this is the charge on a proton because it's positive. The charge on an electron would be negative, 1.602 times 10 to the minus 19. So how did he do it? Well, here's the apparatus. So what he did was he had two parallel metal charge plates. So you can see a metal plate here, a metal plate here. And he balanced charged oil drops in a uniform electric field. So he sprayed these, like I've mentioned this before, but if just imagine a spray bottle creates like fine, like misty droplets. Well, an atomizer can actually produce droplets like kind of even smaller, like way smaller than you might see with a spray bottle in water. But the idea is basically squirting oil through this atomizer created very, very, very tiny oil droplets. And they were allowed to float through a hole, a little pinhole, into between these metal plates. And the idea was if you connected these plates to a battery and created an adjustable voltage between them, because the atomizer via friction often imposed a charge on the electrons, some positive, some negative. When they fell through the pinhole, if we had the oil droplet's own gravity wanting to pull it down, but if the charge was the right sign, the plate at the bottom would be repelling it, and the plate at the top would be attracting it, and there would be a force acting up on the charge, and they'd be balanced. And if you could determine the mass of the droplet, you could figure out what the charge was on the particle. So I'm going to add a couple notes to this diagram, things that I've mentioned. So for the atomizer, the note I want to add here is that friction gives charge to the droplets. So if the friction removed electrons from a oil droplet, if you have less electrons than protons, you're going to have a positive charge. But if an oil droplet gained some electrons, more electrons than protons would have a negative charge. So some have positive, some have negative. And I have a little note for over here. So by adjusting delta V, the voltage, that varies the electric field. The uniform electric field, remember parallel plates, uniform electric field, varies the uniform electric field. I'm going to add in brackets here too, and the force. So you can imagine you have a droplet coming down, gravity pulling it down, and you have some electric force acting up on it. If the sign is right, if the oil droplet had a positive charge and we had positive and negative plate, then that would be exerting a force up. All the charges that had a negative charge Nope, they would just float down, no big deal. But by varying the voltage, so just having a knob where they can vary the voltage, you could increase or decrease the force. And so eventually you could match up. You could vary the voltage until that gravity force matched the electric force, and an oil droplet would just sit there. And he would be looking through his microscope, adjusting his knob, being very careful until he suspended an oil droplet or some oil droplets in air. So as I said, he adjusted the voltage until he had one drop suspended in the electric field. So you can see here in this diagram, we've assumed that the positive plate is on the bottom and the negative on the top. So that must mean the oil drop that was suspended had to have a positive charge for its electric force to be up. If he switched the voltage around, so we had a negative plate on the bottom and a positive on the top, if he had suspended a charge, we would know it was a negative charge. But the way the diagram here is set up, we know that there was a positive charge, that this oil droplet had lost electrons. I mean, this is our starting point. So when, in this case, when everything is balanced, so when the oil drop is balanced or suspended, the sum of forces is 0. And so what we have then is we have that the electric force is perfectly balancing the gravitational force. And electric force in a parallel plate, uniform electric field, just like Fg is mg, Fe is q epsilon. Now we're going to make use of our last lesson. The electric field, hard to measure, but the voltage, easier to measure. And we actually have an expression for the that ties electric field, voltage, and plate separation together. It was delta V equals epsilon times R. So epsilon is delta V over R. And so by rearranging this, Q equals M times G times R over delta V. And so the idea is, if you knew all of this stuff, G and R are pretty, G is just acceleration due to gravity. R is the plate separation, easy to measure. Delta V is easy to measure. Then we could find the charge on the droplet. The difficult part was, how do you find the mass? So we won't actually go through the math behind it. To find the mass, what he did was, so having suspended in the field and found that required voltage, he turned off the electric field, and that oil droplet was going to float to the ground. Now, you guys in your grade 11 course hopefully talked about terminal velocity, but in reality, with air, things just don't accelerate forever. They actually reach a point where the air resistance matches the force of gravity, and they fall at a constant speed called terminal velocity. Well, a very fine oil droplet, like if you guys notice when you do a spray bottle, the drops in the air, they don't accelerate down like you were dropping a ball or something. They just float down, and they reach a terminal velocity actually very, very fast. And so by measuring this terminal velocity, he could find M using the density of the oil droplet, the surface area of the oil droplet. That's basically the long and short of how he did it, but we're going to just spare ourselves the details. But that was the tricky part, but that's how he found the mass. And so, yeah, if you know the mass of the droplet, G, the plate separation, and the adjustable voltage, you can find the charge. So what did he find? He found all the values for Q. So he did this experiment over and over and over and over and over and over, and got lots of values for Q, hundreds, maybe even thousands. But what he found was that all the values for the charge on all the oil droplets he got, they were all an integral multiple of 1.602 times 10 to the minus 19. So I mean, they were all integer multiples. So it was either 11 times Q or 33 times Q or whatever. They were all multiples of Q. So if a charged particle has one extra or loses one electron, its charge, we're going to say, is going to be E. The elementary charge (1.602 times 10 to the minus 19 coulombs. So the charge on any particle is always a multiple of this value, E. So we, just like we use G is 9.8, this constant E, we can think about it as 1.602 times 10 to the minus 19. If we're talking about an electron charge, so if we have one extra electron, the charge would be negative E. If we have one less electron, so one more proton electron, the charge would be positive E. So we're just going to do a couple of examples. So one, just getting used to this fundamental charge. So let's say we have a small sphere with an extra 5 times 10 to the 14 electrons. Well, what's the charge? So we can do that. So the charge, Q, is always an integer multiple of the fundamental charge. Now I'll ask you, if we have an excess of electrons, is our charge going to be positive or negative? And because we have extra electrons, more electrons than protons, it will be negative. So I'm going to plug in negative 5.0 times 10 to the 14. And E, 1.602 times 10 to the minus 19. And again, negative since we have excess electrons. And remember, electrons have negative charge. So this is just a pretty simple plug and play calculation. Times 1.602 times 10 to the minus 19. So that is negative 8 times 10 to the minus 1, 2, 3, 4, 5 coulombs. So that'd be the charge. Let's try another example. This one we're going to look at a Millikan-type experiment. So we have two plates, 2.5 centimeters apart, and we have a latex sphere. So a very, very small, like if you think about, I think we've banned these in Canada, but you know how certain shampoos used to have those micro beads, I guess, to like have like a scrubbing, feels like you're scrubbing in the shower, those like little small beads. Those are just little latex plastic beads. So imagine one that's very, very, very tiny, 1.5 times 10 to the minus 15 kilograms. So just like Millikan and his oil droplets, this latex sphere is suspended between these two plates. And when the potential difference is 460 volts, and we're told the upper plate is positive here. So let's actually just draw this out. So the upper plate, positive. Lower plate, negative. Potential difference of 460 volts. So the difference in potential from the low region, negative, to the high region, 460 volts. And we're told the plate separation, 2.5 centimeters, so 0.025 meters. And we have this latex sphere, and gravity is suspending it down, electric force suspending it up. Now we can answer part A. Is the sphere charged positively or negatively? What do you think? Well, since it's being repelled from the negative plate and attracted to the positive plate, we know that the answer to part A is it's a negative charge. I don't think that shows up okay. So let's calculate the charge in the sphere using Millikan's experiment. So we don't need to rederive that expression for Q. We already did that. It was mgr over delta V. So let's just make use of that. If we know all these things, we can find the charge. So we had 1.5 times 10 to the minus 15, 9.8, 0.025, potential difference, 460 volts. So something you're going to notice is potential difference is always given, okay, I'm not going to say always, but 99% of the time, the potential difference between two plates, it's always the difference from the negative plate to the positive plate, the low to high, so it's always a positive. And so in this calculation here, everything we get is we're getting a positive. Because remember, in the way we calculated the electric force, Fe equals Q times epsilon, remember that gave magnitudes, right? So what we're finding here is the magnitude of Q. So just keep that in mind. And we've already reasoned out what the sign would be. It's going to be negative. This is a negatively charged particle. 9.8 times 0.025 by 460. All right, so I got pretty much 8 times 10 to the minus 19 coulombs. All right, so how many, we know the charge is negative 8 times 10 to the minus 19 coulombs. So for part C, so we've reasoned out the charge is negative because it's being repelled from the negative plate, attracted to the positive plate. A negative charge must mean we have more electrons than protons to have that negative charge. That means we have an excess of electrons. And how many excess electrons do we have? Well, if Q equals N times the elementary charge, then to get the number of electrons, we just take the charge and divide it by E. So let's see how close we get here to a value. And so we can just go back and plug in the size of the charge, 8 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19. Last time I checked, that was 5. So 5 excess electrons. And that's the Millikan experiment, everybody. And that kind of brings today's lesson to a close. So a little bit of a lighter material for sure, but really cool. This is how the charge on the electron and hence the proton was determined with not overly complex instruments. So pretty neat. What's next? We're going to tie in some conservation of energy ideas to look at the motion of charged particles. So we'll look at the motion of charged particles for, say, 2 point charges brought together and, say, imagining they were free to move. So what would happen if we let them go? How would they move? How fast would they get over a certain distance? We'll also look at the motion of charged particles inside parallel plates where the force and the acceleration is constant. So we'll have kind of 2 different scenarios there. Until then, though, hope you're staying well. Have a great day, and we'll see you soon.